Hello and welcome back to numerical problems on compression member. Hope everyone is doing well and spending a lot of time, in fact more time on career enhancement than entertainment. Right, so in this we'll take up the numerical to calculate the design capacity of a column, and in the another set of problem we'll design the axially loaded column as per IS code. So there is a quiz. Most of the students are confused with what is epsilon. Number of times we are using this term epsilon. It is nothing but yield stress ratio, and for Fe 410, which we are generally using in our numericals, value of Fy is 250 Newton per millimeter square or megapascal, right? So epsilon is nothing but under root 250 upon Fy. So when we calculate it, works out to be 1 only. So this thing you should keep in mind. What is epsilon? It is yield stress ratio. Okay, so coming to the concept of design of compression member, there are three things. First one is the load on the member. See, load on the member, either it is given in the numerical or we need to calculate the capacity of the section. Next important thing is the resisting area. Suppose if the load is more, we should provide more area. If the load is less, we'll go with smaller area. But safety and serviceability, both criteria should be satisfied. Another concept is the permissible stress. Depending upon the material, E and I of the material. E is the modulus of elasticity and I is the geometry. It is I section or it is hollow section, it is built up section, like this. So now what we'll try to find what is the relation between this stress load and resisting area. To calculate permissible stress of a section, we need to know the geometry. Other geometry which we should know is the value of lambda, that is slenderness ratio, represented as KL by R minimum, right? So it is given in table number 9 from page 40 to 43. You can open this code IS 800 2007 page 40. There you will see that table 9 is there, and table 9 has 4 subparts: curve A, curve B, curve C and curve D. So first thing we should know which curve we have to use. It is similar to section classification which we used to do for flexure member, but here we are doing buckling classification. Now the value of FCD essentially depends upon slenderness ratio and buckling curve. So KL upon R. What is KL? It is the effective length, and what is R? It is the radius of gyration. So load on the member is either to be calculated from the section that is given, or we have to design the section by the value of load that is given in the numerical. So slenderness ratio is inversely proportional to R minimum. So if we take the value of minimum value of R minimum, we will get the higher value of slenderness ratio. And what is the relation between FCD and slenderness ratio? You can easily check that table. As you go down on the table along the column, you will find that as the value of lambda is increasing, value of FCD will reduce. So this is our first question. This is question number 7.2 from SK Duggal, and calculate the design compressive load for a stanchion. Stanchion is nothing but column only. In UK people use this term. So IS HB 350 is the section. It is 3.5 meter high and the column is restrained in direction and position at both the ends. It is used as an uncased column in a single story building. Use Fe 410. So whenever section is already given, so we'll call it as an analysis problem, right, in which section is already given and we have to find the capacity of the section, how much load that section is allowed to carry, right? Now what we have to do, calculate the design compressive load for a stanchion. Now this is a very important line, as we have already seen that FCD depends upon the geometry, that is KL by R. So this data is essential to calculate the value of KL. So 3.5 meter height, the column is restrained in both directions, right? So this is an important line for finding the value of KL. Now we know that from the relation between load and stress and area, we know that load will be equal to effective area into FCD. So AE, that is effective sectional area, will be found, can be easily found from the steel table for this section IS HB 350. So the main issue or main challenge in the numerical is to calculate FCD, and to calculate FCD we should know the value of KL. So these are the steps, very simple step, one line steps are there. So already calculated FCD. See, these steps we have already done in when we were designing stiffeners, right? So this is nothing new for us, we have already done this. So first thing is we calculate effective length, then we will calculate radius of gyration. Radius of gyration we have already done in the days of first semester, probably in the days of mechanics. Then we will calculate, divide this KL by R minimum. Then we will check which section classification or which buckling curve we have to use to find FCD. So start with step 1, value of KL. So check the end constraints. Effective length depends upon the unsupported length and the end constraints. So the column is restrained in direction and position. So it means fixed, because restrained in direction means rotation and restrained in position means translation. So the column is not allowed to rotate, nor it is allowed to change its position. So it is a case of fixed case. So what is the value for column with both ends fixed? So recommended value is 0.65. Recommended value is 0.65. This is given in page 45 of IS code. Then next step is to calculate radius of gyration. So as per new IS 800 2007, the nomenclature for axis of member is changed. Now this axis, which was earlier named as x-axis, is now referred to as z-axis. So this is y-axis and this is z-axis. The old printed versions of steel table will still refer this axis as x-axis. So don't be confused. You have to be aware of it, that in some cases we will take the value of RXX from the steel table because it is old printed version of the steel table. So how we will find this value RX, RZZ and RYY? It is directly taken from the steel table. So now we'll compare what both of the values are there. So we'll find that radius of gyration along about y-axis is minimum. So when we calculate slenderness ratio, we'll use R minimum, right? It will give critical value for design compression member. So substituting the value of KL, that is 0.65 into unsupported length 3.5 meters divided by RZ, we will get the value of lambda ZZ. It is 15.53. Any guesses for what will be the unit of slenderness ratio? It is length by length. So slenderness ratio is a unitless quantity. Similarly, we will calculate it for lambda YY, that is KL upon RY. RYY is 52.2. So like this we will get the value of lambda ZZ and lambda YY. Remember that as a designer we are focusing on the critical value. We are not interested in maximum or minimum, we are interested in to find the critical value. So lambda max means the higher value will give us the critical value for design compressive strength, and minimum radius of gyration is used to calculate maximum slenderness ratio. So if you want to calculate maximum slenderness ratio, you will use R minimum, right? And we know that the behavior of column is a function of slenderness ratio. Now we come to buckling class of the cross section. So first thing what we have to check is what is the ratio of H by B. What is H? H is the total height, and what is B? B is the width of flange. So simply divide height of the section divided by width of the flange, If it is greater than 1.2, we'll use this, and if it is less than 1.2, we'll use this. So in our case, h is 350 and b is equal to 250. So when we solve it, we get the value of h by b as 1.4, which is greater than 1.2, and thickness of flange is also less than 40 millimeters. So we can say that buckling about z axis will be taken from curve A, and buckling about y axis is considered as will be taken from buckling curve B, right? So this is to check whether we have to use table 9A curve or table 9B curve. So about z axis we will use A curve, and to calculate about y axis we have to use B curve. So here h by b is greater than 1.2, so we'll see that zz axis, along zz axis buckling curve we use is A, and for y axis it is y. We'll put this FCD, and to calculate FCD along zz axis we'll use lambda zz. What is the value of lambda zz? We have already calculated it. It is 15.53, and curve we have to use for z is A. So in curve A, 15.66 will be somewhere between 226 and 227. It will be here. And for FCD along y axis, it will be lambda yy KL upon RYY. It is equal to 43. For y axis, we should use curve B. So it is given in page 41, curve B, and it is 43 somewhere here. So it will be FCD yy will be 201.7 between here, right? And see, in this is a consolidated version of the values for FY 250, but you have to use separate curves, and this is the way it is given in your IS code, right? So now when we have calculated FCD along ZZ axis and YY axis, we will calculate the design strength. So as we can see that the minimum of the two will give the design strength. So we will multiply AE, that is taken from the steel table, with the permissible design stress. It is 201.7, and to convert it into kilonewton we will divide it by 1000. So this is a very simple problem.